So welcome, everyone. Thank you so much for joining us today. This is a talk called Taking Elixir to the Metal with Rust. My name is Sonny Scroggin. I'm an Elixir developer, also Erlang as well, obviously. But I'm really excited to talk today about this because it's been something, there's a project that I've been working on to kind of integrate the two together so that you can take advantage of the wonderful things that each of these languages provide. And so for those of you who are not familiar with Elixir, it's a dynamic functional language. It runs on the Erlang VM. And it's a fascinating language because of the fact that it's got this Erlang VM and it has been around for 30 years, and it's been known for building scalable, fault-tolerant applications. And so you kind of have this holy trinity of these three things of concurrency, fault tolerance, and distribution that Erlang provides that kind of allows you to build systems that don't go down. If processes crash and things like that, you will have something that actually restarts these things and allows you to keep your systems running for long, many years at a time. So, but one thing that I think that people aren't familiar with about Erlang is that it's really an integration platform. And earlier this week, Brian Hunter was speaking about interop between F# and Elixir, and how the Erlang VM really provides a lot of ways for doing that. And so, you can use things like ports, which are essentially like pipes, where you talk to other programs via standard in, standard out. You also have something called Erl interface. And Erl interface is a C API exposed by the Erlang VM that allows you to kind of talk to external programs with Erlang's distribution protocol. And that opens you up to be able to do all kinds of interesting things. So C nodes are a version of that where you have a C program that uses Erl interface. And so from the Erlang VM, you can actually talk to a C program like it's actually an Erlang node. So really interesting stuff. There's also stuff like port drivers, which the files, like if you need to talk to the file system, it goes through a port driver. And so those are all implemented in C. So they're all kind of native functions. They have really fast execution and stuff like that. And then we also have native implemented functions, or NIFs for short. And those simply are native functions that you can call. So some integration examples, the mix tool with Elixir. We'll use ports, for instance. If you have a dependency in your application that uses Git, it'll actually use the Git on your system to go and fetch the dependency. Another cool example is the inet driver in Erlang. It is a port driver which allows you to do networking, so TCP, UDP, all that kind of stuff. And of course, it's written in C as well. And then an example for as a NIF is this library called Jiffy, and it's a really nice library that does JSON decoding and encoding and stuff like that. And that's all implemented in C as well. So this talk is going to focus on writing NIFs. And NIFs are, as I said before, native implemented functions, is the acronym. And they are usually implemented in C or C++. And obviously, with that, there's a lot of unsafe things that can happen. And so it is a feature that is reserved for wizards, people who know what they're doing and are going to not do things like null pointers and out of bounds checks and stuff like that and crash your VM. So when you write NIFs, it comes with this gigantic warning. That's basically, I'm not going to read it, but it's essentially you are in the land where you have to be safe and you have to be very careful. Otherwise, there are consequences for your actions. If you write a NIF that crashes or causes a seg fault, you will crash the entire Erlang virtual machine. And that obviously is a big problem when you are writing fault-tolerant applications. You can't guarantee fault tolerance anymore because you have some C program that actually takes your whole program down. So NIFs, they can be called just like any other Erlang or Elixir function. So you have a module that has functions inside of it, and anytime you call a function on that module that is a NIF, then it gets the native code gets executed. And so NIFs live in a dynamically loaded library, so a shared object or a DLL for Windows, I think, is what that is usually. I'm not familiar with Windows stuff, so. But NIFs, when the module is loaded, actually ends up replacing the bytecode that would normally be written in an Erlang module, and replaces it with native code. So the NIF functionality itself, there's an API that allows you to read and write Erlang terms. You can there's like some special operations for doing binaries. There's also these things called resource objects that we'll talk about. And it also has some functions for doing threads and other concurrency features. So to get started, if we were to kind of create something like a JSON module, we could have this onload module attribute. When Erlang is loading this module, it's going to hit this attribute here, and it's going to say, hey, I want you to call the init function when you're loading me. And so this init function is now going to find the path to our dynamic library, and then call Erlang load NIF with the dynamic library. And then these are the functions that you would put them in your module still, so encode and decode, but you can just simply throw an error or something if it was ever to be called and the NIF is not loaded for some reason. And these are the functions that will be replaced by the native code. So why would you write a NIF? They seem unsafe, right? So, but really, Erlang was not designed for sheer raw CPU speed. It was designed so that you could have a nice, consistent runtime where everything performed, pretty linearly. If the more processes that are in the system, you can understand how the system is going to perform at scale a lot easier. And so, if you need to talk directly to hardware, there's no other way to do it than to use kind of native code. If you have you need to interop with some graphics library, you'd want to do that in some native code. And maybe the functionality that you need already exists, and maybe it doesn't already exist in an Erlang or an Elixir library, but it exists in some C library, and you just want to use that functionality because rewriting it in Erlang would be, too costly or whatnot. So let's take a look at the structure of a NIF in C. Generally, you're going to include the ErlNIF API, so from the header file. And all NIFs have this signature. So it takes, the first argument is a pointer to an ErlNIF environment type. It's got an integer which says this is how many arguments I take. And then you have an array of NIF terms that are going to be, the length of that is going to be the count of the integer of the argc. And then the function itself just needs to return an ErlNIF term. So this NIF environment is essentially what when you call a NIF, this NIF environment is it's essentially the environment of the calling process. And so it represents the calling process itself. It's got some transient information that you would never really interact with itself, but it's an opaque type. And it allows you to essentially create terms and decode and encode and stuff using this environment. And the Erlang NIF term is very similar to that, where it's opaque. You can use it. You have to pass it into all the API functions, and you can test to see, hey, is this term an atom, or is it a binary? Is it a Boolean? You can have just different functions that will test those things and such like that. And there's one thing that's interesting too when you read the documentation. The documentation actually talks clearly about the lifetime of terms and an environment. So terms cannot live longer than an environment that they're bound to, and we'll see how that plays out in Rust later. So the next thing in a NIF is you're going to say, hey, these are the functions that I export, and you provide this. The first thing here is, you have a encode, and then which is the Erlang function name or Elixir function name, the arity of the function, which how many arguments does it take, and then it's basically a pointer to a function in the NIF itself that it's going to call when it does it. And then you just simply load it with Erlang NIF init, and you can see here you pass in a module name for where it's going to actually live for that code. And so for all Elixir modules, if you're not familiar, when you create a module in Elixir, even though I created a module called JSON, when it actually compiles into the Beam code, that module name is elixir.json. So that's why we have that there. All right, but I don't know about you, but I am not a C programmer. I don't know how to do any of C programs. I would not trust myself, if my life depended on it, to write a safe C program. But Rust is here and promises a lot of great things to help us along. The compiler is absolutely amazing. It essentially will not let you write a program that will cause dangling pointers or unbound checks and things like that. And so it's really fast, and it keeps you safe. So it causes the compiler will not let you compile a broken program, essentially. It doesn't mean that the logic is correct, but it will at least compile and guarantee safety. So some other things that stand out with this here. This is the list on their website, of the kind of bullet points of what it does. And so it's got like zero cost abstractions, guaranteed memory safety, threads without race conditions, which is a great thing. There's also pattern matching, which is similar. We use pattern matching in Elixir and Erlang, which is nice. So it's a nice match. It has type inference as well, which is good. And it also, the bottom one here is efficient C bindings. So the Erlang NIF library, from Erlang is written in C, and so that means that Rust can actually be a wrapper around that and actually use it directly. And so this allows us to use NIFs written in Rust within Erlang or Elixir. And so that brings us to this project here. It's called Rustler. And it was started by this guy, Hans Josephson. And just a couple months ago, I went out on a journey looking to do this, and I found this project. And at the time, it wasn't compiling correctly for Macs. And so I took it upon myself to make a couple of pull requests to fix a few things and became a collaborator. So this project is really, really fun, and it's now allowing us to build NIFs in Rust, which is nice. So Rustler itself is, obviously a library for writing Erlang NIFs in Rust, but it provides facilities for generating boilerplate and things like that makes it nice to get up and running and get started really quickly. So it handles encoding and decoding terms from Erlang terms to Rust types and Rust types back into Erlang with just a simple function call, which is really nice. It catches any Rust panics that might happen for unhandled things where you actually say in the code that I don't know what to do here, so I'm just going to panic. If you do panic in your Rust code, it will catch those before it unwinds back into C, causing a seg fault and blowing up the VM. And so the goal really is that the code that you write in a Rust NIF should never crash the Erlang VM. So to get started, you just simply create a new Elixir project with mix, so mix new, and then your project name. You install or you add the Rustler dependency. Right now, this is going to be the next version that's published, 0.12. But for now, what you can do is you can use master. You can just pass in GitHub and the kind of username and repository there. And then because this project has both the Rust code and the Elixir code all in one repo, you can use the sparse option to specify the path to the actual directory where the Elixir project is. So then you would fetch your dependencies, mix deps.get, and then Rustler provides this rustler.new task, and it'll just kind of prompt you through, like, hey, what's the name of the module, and what is the name of your Rust library that you want to create? And so in this case, we have a module named JSON, and I'm calling the library fast.json and overriding the JSON because we'll actually be using a Rust crate called JSON, and we can't have the name collision there. So then you just need to add the compiler, the Rustler Compiler. It essentially is a compiler that's written in Elixir that keeps track of where the files should go and invokes the Rust compiler with the right flags and things like that, so which is nice. And then we just set up this option here called Rustler crates, which we call this function here. And this function just sets up some configuration for the crates themselves, and that's what you call a Rust library. They call it a crate. So this just shows, the path and also the mode in which we want to invoke the Rust compiler. So if we're running in dev mode in Elixir, we'll probably just want to compile the Rust code with the debug mode so that it's a faster compile time. But if we're running in production, we want to release it with the release mode so that it's better optimized and all that stuff. But the compiling step takes a little bit longer. So if we go back to our code, this is what we had before. And with Rustler, it becomes this here. So you just say use Rustler, give it the name of your application, and then it can go ahead and find the crate that you intend to use. You could also, with a project, have multiple crates within your project. And so in that case, you can also specify a crate name that you want to use, and it will go ahead and find that. So, we go from this to this. So much nicer. All right, so let's take a look at some Rust code. So the main file is lib.rs, and in here we're just using extern crate, which says, hey, I'm going to use an external library. So we're calling Rustler, and another one called lazy static, which is for creating our atoms and stuff like that. And right here we're using also the JSON crate, which is an external crate from the Rust community that does JSON parsing and stuff like that. So right here we're just taking advantage of a library that already exists. I don't have to go and write a JSON parser, which is nice, right? Here we have a couple of other modules in our project, so the decoder for calling the decoding. And then we just export. So we have this macro called Rustler export NIFs, and you provide the name of the module. You provide the kind of exports themselves, very similar to the CNIF. So we have the function in the module for your Erlang module or Elixir module. You have the arity, and then you have the Rust function that you're going to call. And then this none down here, that is if you have additional things that you need to do when the NIF is loaded, you can do it in another function, and you can provide. So this none, if you're not familiar, is kind of a monadic type where it's an option type. So it's either something or it's nothing. So in this case, it's nothing. But if we did want to provide a function, we could just call sum and then pass in the function that we want to call. And we'll see the example later on with that. So the simple approach, or the naive approach, is simply just use an existing Rust JSON parser. That way we don't have to do any extra work. We're going to take in a string or a binary from Erlang's side, and we'll convert that into Rust types, and then we'll convert the Rust types back into Erlang terms. So this is the decoder, and all NIF terms. This is the decode function here is this is the signature here. So it takes the environment right here. It also takes a vector of NIF terms as arguments, and then it returns what's called a NIF result, which of NIF terms. And you'll see these tick A things in there. Those represent annotations for lifetimes. So it helps the Rust compiler know that when something can outlast the other thing. And so all of these things are kind of bound to the same lifetime across the board. So, all right. So the next thing is we just grab out the first argument from the vector. So we can say args0.decode, and that will return us the actual binary itself. And then we can use pattern matching when we're calling this JSON parse function. We pass in the data, and then we will either get, so it returns a result. So we either get OK or an error. And this is also very, very common and similar to how you use Erlang and Elixir. A lot of functions will return a tuple of OK and the value, or an error and the reason. And so this is actually kind of plays very well together. And so if we get a good result, then we get some JSON types back. And now we can call a function to turn those JSON types into Erlang terms. And then we will just return, right here, we'll return a tuple of the atom OK and the actual result of calling that function. And that will end up being returned as the result of the function. In the case of an error, we'll just return an error tuple. So that JSON to term here is just essentially a recursive function that if it has an object or an array, it recurses over all of the items in of those things, and essentially gives us one data structure back, and then we can send it as the result. So, and all of these are simply just calling encode on all of the different types, and turning the raw Rust types directly into an Erlang term. So let's time our NIF. So if you get if you run this on like really small inputs, it's going to be fast and it's going to be performant and nice. But when you get some like big data, you have some big JSON file. This one here is like 8 megabytes. And you run it and you time it, then we get something like this, which is really bad because it took almost 1.5 seconds. So 1.5 seconds of CPU, blocking the CPU, blocking the scheduler in Erlang is a bad thing. But why is that? So in order to really understand why that's bad, let's take a look at the warnings a little closer that you get here. So a native function doing any lengthy work, it doesn't really specify how long that is, but before returning, degrades the responsiveness of the VM, and it can cause miscellaneous strange behaviors. This is actually verbatim out of the docs. So such strange behaviors include, but are not limited to, extreme memory usage and bad load balancing between schedulers. So again, let's take a little bit deeper dive into the Erlang VM and see how this architecture works and why we need to be careful when we're writing NIFs. So if you have a machine, and that machine has 8 cores, then you have the operating system and kernel threads on top of that. And then if you start the Erlang VM, you have one Erlang process, and that Erlang process VM process is going to then spawn a scheduler thread for every single core on your machine. And each of these cores now, or each of these schedulers rather, has what's called a run queue. And it actually, in reality, has more than one queue, but the main one is the run queue. And the run queue basically holds all of the Erlang processes that are going to be executed. And so you have a queue here, and it just pops off the head of the queue, runs the bytecode that that process is supposed to run. And if it reaches some code, some opcode that says, hey, I need to get some file I/O, or I need to make a network call, or I'm waiting for a message from some other process, then the Erlang VM can preempt and actually stop executing that process and move it out into another queue until that message arrives for that process. And so then it can pop that one to the back of the queue and then pick the next one off and keep going. And so it can either do that for, like, if it's going to do a blocking operation, or it also has this thing, it has a limit of things that it can do. So it gives each process what are called reductions. And you get 2,000 reductions, and then your talking stick is taken away until the next time you're scheduled. So, and this essentially, a reduction is roughly equivalent to a function call. It's not exact. Oops. So one thing that's interesting is that the schedulers actually use this thing called thread progress. And there's a really interesting article or markdown document in the Erlang repo that you can read here. And thread progress is quite an interesting thing. Instead of using, the schedulers themselves, they share some data structures. And so when you have shared data, you have, definite problems of race conditions and corrupting memory and things like that. So instead of protecting them with locks or ref counts, which don't scale very well, instead they actually frequently kind of give a progress report out to all of the different schedulers. And so what that does is it allows the schedulers to understand what work has been done, what data structures are still being used, and when it's okay and when it's safe to actually get rid of stuff. And so if you block the scheduler, that's really, really bad, because now you block thread progress, and it makes all of the other schedulers wait. So if you block even just one scheduler, you can now cause the other schedulers to have to wait around to ensure that memory safety is happening within the VM. And also, another big problem is that if you block a scheduler, all the other processes that are in that same scheduler can't run. So a NIF should never take longer, should never block the scheduler for more than 1 millisecond, is what the documentation says. Now, 1 millisecond in CPU time is like an eternity. So even that feels really, really long. So, so when you're writing NIFs, you should also count reductions. And there's a way to do that, but a lot of people don't actually do it because it's been introduced quite recently. So, so one way we can count reductions in our code, just to test to see how our NIF is performing, we can write this function here. We just basically send ourselves a message in the end. We get our start time. We're spawning a new process to actually run the calculation or run the computation. And we get the reductions, the starting reductions for that process. We run the function with the data. We get a time difference. We get the reductions afterwards, after running it. And then we send the parent process a message that just basically shows us the time and all that data there. So, and then we just wait for the actual result here. So when we do this with our big data, we can see it took 2 seconds. We started at 6 reductions. We ended at 16 reductions with a total diff of 10. So we have 2,000 reductions, and reductions are a way that kind of help the VM understand how much work you're doing, how much time it's going to take you. And when we don't have proper reduction counting, it throws everything off. And so this should be much, much higher with running and blocking the schedule for 2 seconds. So we can do better. So one option is chunking. So rather than calling a NIF once and waiting for the result, you can hit it once, it'll return you back a partial result. You can keep kind of chunking it and calling it recursively. And then that way, when you are returning on the Erlang side, the Erlang scheduler now can preempt the process in the middle of what it's doing, and then you get kind of much more better behavior out of it. So in order to do that, though, we can't use that JSON crate. So we have to actually do some work. We have to build a parser. So this way here, what we're going to have to do is we're going to have 2 NIFs. We're going to have one that initializes and then calls the second one, and then can allow us to actually call this iterative NIF over and over and over again. So what we do here is we have our decode init and decode iter, and right here in decode we pass in the data, and we pipe this data into decode init, which then will call the NIF decode init, and it will then internally call decode iter. And when we get a result back, if we get this more tuple here, we can now take the data that's returned from that and keep chunking it over and over again in a loop, in a recursive loop. So this is going to require us to learn about something else, though, which is pretty cool. It's called a NIF Resource Object. And resource objects are essentially like a safe pointer. It's a safe way to return pointers to native data structures within Rust or C or whatever from a NIF. And it can be stored, it can be passed around to it can actually be passed from process to process, it can be passed and shared amongst processes. You can actually make copies of it and things like that. And so you can have multiple processes actually having the same resource, which is actually quite an interesting thing when you think of Erlang with immutability and stuff like that. Because now you have this handle to something that you can actually kind of almost mutate inside the thing. And really the end result of a resource is to pass it back into Erlang so that it can continue to be used over and over again. And a resource object is not deallocated until there's no more processes having reference to the data structure. So this is going a step further. We have now a parser and a sync to store terms. We have our decode init and iter. And now we're using the sum and load now. So we have a load function where we actually need to initiate our resource object. So we have a special struct called parser resource, and we now have this allocated so that we can use it within our NIFs. And so decode init, simply we have this parser resource which holds a mutex of our parser struct. And obviously we need to have a mutex because the fact that those resources can be shared with multiple processes. And if you have 2 processes on different schedulers running at the same time, then you have the possibility of data corruption, things like that. So you have to be safe and careful. So with decode init, we do the same thing as before. We get the source. We create this resource. And this, I wish Rust had the pipe operator. That would be really cool, because then you could write this much nicer. So reading it inside out, we're creating a new parser from the source, wrapping that in the mutex, putting that into the parser resource struct, and then we're creating this resource self that comes from Rustler. And then we create a new empty vector, and we send it into decode iter, which is another NIF. So what we've done here is we've set up the arguments for passing in and calling decode iter by just essentially making them up here on our own. So when this gets called, we now have a resource that we can grab, and we can decode that. We get our sync stack, which is essentially, it's a place to hold terms outside of the parser. because the parser is going to be stored in the resource, and it can't have access to terms or the environment that are going to be that are not going to outlive the call of the NIF call. So we have to separate those and make sure that they are two distinct places. So we create this sink so that we can stick our terms in. We have to get a lock on the mutex for the parser, and then we use this thing called consume time slice. So consume time slice allows us to report reductions kind of to the VM. Every time we call it, the VM is going to tell us whether or not we're up, like our time's up. So if it returns false, then it will go in and it will actually parse. It'll do some work. So it'll call parse on the parser, and if it returns OK true, then we return the result of the end of it. If it returns false, that means it's not done parsing. There's still more stuff to do. So return continue. And then if there's an error, return the error. If we end up getting where consume time slice returns true, that means your time is up, you're done, you got to give over the talking stick. So we return a 3-tuple of more, and then the resource itself, and the current stack state of the sink. And these are these terms that we can now act and treat as an accumulator for the chunking. So the result of this is much different. So we now have a diff here where we actually are doing 11,300 reductions, which is much, much better. We didn't block the scheduler, and probably didn't block the scheduler. But this is definitely much more on track. It still took a long time, but we were a good citizen of the beam, which is nice. So there's also a way that you can do what's called rescheduling, or they call it yielding. And there's a function in the NIF API called enif schedule NIF. And you can, if you were to combine it with the consume time slice, it allows you to, instead of having to return back to Erlang or Elixir, you can simply just reschedule another NIF call internally. So instead of chunking from the outside, where you have to call the NIF from Erlang over and over again, you can actually do that within the NIF and have the NIF rescheduled likewise. So unfortunately, right now, it's not available in Rustler, and simply because it's unsafe to do so right now. One of the goals of Rustler is to make sure that you can't do things that are unsafe and cause crashes and cause bad things to happen. And so until we can find a way to support this in Rustler, we got to kind of do some other stuff. But I'm sure eventually we'll be able to get it in. It's just a matter of the documentation specifying that you have to do these things in order to do it, and if we can't guarantee at compile time that you are using it that way, then we don't want to put it in the library yet. So that brings us to another option, which is threaded NIFs. So simply, you can call a NIF. That NIF spawns an operating system thread to do the work, and once it's done, it will send your process a message. And so what's cool about this is we can go back to using the JSON crate, which simplifies our code, because we don't have to manually create a parser that we have to maintain that's slower than the original one anyways. And so this one's called decode threaded, and same as before, we get the source. We spawn we call this thread spawn from the Rustler crate, and it takes this trait called the thread spawner. You pass in the caller. So if you notice up at the top, the NIF environment, it's still a NIF environment, but I've named it caller to specify, just so that we have, because we also have an env variable that's passed into this closure over here. And so to keep the two kind of distinct, I used the caller as the variable. So this passes in the caller, and the caller is an environment for the calling process, and we can just get the PID, or the process ID, of the calling process, so that we can actually send a message to it from what's returned in our value here. So we can just call JSON parse on that. We get the value that's returned there, and then internally underneath, it's going to send that value to the process directly. And then here, we're just returning immediately after this thread spawned. So we return back to the caller just an OK tuple to say, OK, I did the thing. Now you can go ahead and wait. And this would be the Elixir code that you would write in order to do that. So you'd have your decode. You'd call decode threaded, and then you would just wait in a receive block for the result. If you get OK result, then you're good. You return that. If you get an error, you can return that. And if it takes like longer than 5 seconds, then just throw a timeout or something. All right. So another option is dirty NIFs, and dirty NIFs are a way to basically never block the normal schedulers, because you can actually compile Erlang with this enable dirty schedulers option. It's currently an experimental feature, but they are working on it with Erlang OTP 20, version 20. And it should be pretty much stable by then, I think. They're going to try to make it stable. So it'll just be there. You won't have to compile it specially, which is nice. But essentially, it allows you to call NIFs without worrying about blocking the normal schedulers, because in addition to if you have an 8-core machine, as the example I had, if you have an 8-core machine, then if you have dirty schedulers enabled, now you have 8 more threads that are completely separate from the normal way of scheduling processes. So normal processes are just not even scheduled on dirty schedulers. It's only for NIFs that are things that could potentially take too long and block the scheduler. So dirty NIFs, simply you can pass in a flag here, call it dirty CPU. So if it's a CPU-bound kind of work, then you use dirty CPU. If it's an I/O-bound thing that you're doing, there's dirty I/O as well. So there's a couple people I have to thank for this talk. One is the creator of Rustler, Hans Josephson, and also Jason Orendorf, who's a good friend of mine, and he's been mentoring me in Rust. He's actually currently writing the O'Reilly Rust book, co-authoring for that, and he's just an amazing guy. Both of these guys have been really, really helpful in this process, and I'm really excited about what we've been doing. And so with that, I am done. Thank you. And if there's any questions, I think there's a microphone that can be passed around.
So I'll ask you later about the safety concerns with the yield, because I'm curious about that. But I suppose that's longer. But a shorter question was, do you get into any sort of interesting troubles where the fact that in Erlang, when you have the safe references, they can be sort of copied around and stuff, does it interact in any funny way with the Rust sort of ownership checking? Or does it not cause any troubles there?
So the resource itself is stored in such a way that the lifetimes, it's not dependent on the lifetimes. And so it can essentially be a data structure that's in memory that's actually in the VM that's there. And so the Erlang VM will keep a hold of it inside until there's no more, nothing else actually using it, and then it'll just get deallocated. So, does that answer your question?
Yeah.
Okay, cool.
So I had like two kind of minor questions. On the parser, was it just mutating the sync stack when you ran it?
So the sync stack itself, it's essentially just a vector of NIF terms in Rust, and then when you return it, you actually encode it into Erlang terms and send it back to Erlang.
I'll ask you. I want to look at the code in more detail with you just to get something explained, and then I don't think the other question needs asking. I'll talk about it. It's super unimportant.
Cool. All right. Anything else? Awesome. Well, thank you.